So the Sun is here, the fulcrum or balancing point is there, and Jupiter is way out here, 1,000 times farther away.
In space, this means that planets trace out large orbits around the center of mass, while stars make much smaller but still detectable orbits.
Here's a hypothetical planet orbiting a star. In fact, they're orbiting their common center of mass. So the planet moves in a relatively large orbit, but the star also moves, but in a much smaller orbit. So the star moves only a little bit, and the planet moves a lot.
I have a somewhat unusual hobby for an astronomer. I'm a belly dancer and fire performer. But it turns out that spinning fire is a great way of simulating the motion of a planet. And the centripetal motion of your fire on the chain is very similar to the motion of a planet under gravity. The light on my wrist represents the star, and the spinning ball of fire around that is a planet. And as you can see, the ball of fire draws out a large circle, and my wrist is drawing out a smaller circle inside it.
It's this tiny wobble of starlight that scientists use to find extrasolar planets. But even this wobble would be undetectable if it wasn't for the Doppler effect, the fact that wavelengths get shorter as the object emitting them moves toward you and longer as it moves away from you.
The Doppler effect is very familiar if you've ever heard a train going by blowing its whistle. So when the train is coming toward you, you hear a high-pitched whistle. And as the train recedes into the distance away from you, you hear the pitch of the whistle get lower and lower in frequency.
Just like sound waves, light waves appear to shift in frequency as the object emitting them comes toward or away from you. Light from an object moving toward you will look slightly bluer. Light from an object moving away from you will look slightly redder.
When the light waves shift their wavelength toward the blue and toward the red and back toward the blue again as the star wobbles around, the shift is excruciatingly tiny. But it's that difference in the wavelength of the light waves coming at you that is what we measure, and it's what allows us to detect planets around other stars.
Using this Doppler technique, Marcy and Butler spent over a decade patiently studying 120 nearby stars for any sign of a wobble.
I went 11 years without finding a single planet, nothing. And no one was surprised by that. It seemed logical to everybody else that it was a fruitless, frivolous, maybe even lunatic exercise to look for planets of any sort.
But then, in 1995, came the surprise announcement from Swiss astronomers Michel Mayor and Didier Queloz that they had discovered a gas giant planet circling the star 51 Pegasi. Marcy and Butler rushed up to Lick Observatory on Northern California's Mount Hamilton to aim their own telescope at the star and see if they could confirm the Swiss team's results.
Yep. There it is. Looks beautiful. Paul Butler and I were shocked to see that the wobble of the star was precisely as the Swiss had said it was. And I remember driving off Mount Hamilton from Lick Observatory in complete silence, Paul Butler next to me. We knew that the first extrasolar planet had been discovered. It was a very moving, personally moving moment.
Despite the monumental nature of the discovery, this, like all future extrasolar planets, wouldn't get the name of a Greek or Roman god. It would take the astronomical catalog name of its parent star, 51 Pegasi, and add to it a lowercase b. In this standard nomenclature, if a second planet was found around the same star, it would get a lowercase c, and so on through the alphabet. Its name was the only thing unassuming about 51 Pegasi b. The discovery shook the foundations of our understanding of planets. In 1995, astrophysicist Alan Boss was asked to review a paper announcing the discovery by 2 Swiss astronomers of the first planet orbiting an alien sun.
Reviewing this paper caused me a fair number of sleepless nights because it was pretty stunning what they had found.
Stunning because the Swiss claimed to have found a Jupiter-like planet. But where Jupiter orbits the Sun in 12 years, this planet zipped around its star in only 4 days.
And that also meant that the planet had to be much, much closer to its central star, roughly 100 times closer than Jupiter is. And that just was hard to understand.
Jupiter orbits the Sun at a comfortable distance of around 500 million miles. 51 Pegasi b is more like 5 million miles from its star. If it were dropped into our own solar system, this alien planet would orbit much closer to the Sun than Mercury, our innermost planet.
Being so close to the star means that the planet is being literally fried. The radiation from the star is incredible compared to what we experience here on Earth, relatively far from our Sun. So this was a completely unexpected discovery.
It was a planet that could not have formed there. Astronomers knew it didn't belong there. In the same way that if we found a giant redwood in the middle of Central Park, we would know that it didn't belong there. You'd have to ask yourself, how did it get there? And that's what astronomers were asking themselves about these giant planets that they were finding.
51 Pegasi b wasn't just a freak of nature. It was the first of dozens of so-called roasters or hot Jupiters to be discovered in seemingly impossible close-in orbits. Impossible because the accepted theory for how gas planets form suggests that rock and ice in a disk surrounding a young star coalesces into a solid core that then accretes gas, growing larger and larger until it has cleared out all the planet-forming material in its area. This process can only occur at a distance far enough from the star where it's cold enough for ice to exist.
You can't form something that massive that close in to its star. It needs to form past the snow line where ice can form. And in our solar system, that's about where Jupiter is, about 5 times further out from the Sun than the Earth.
So how could a gas giant planet like 51 Pegasi b form so scorchingly close to its star?
It was one of these things where I woke up in the middle of the night, and one night I said to myself, maybe what this means is that this object had to have migrated inwards from where it originally formed.
We now, I think, have an understanding that planet formation is an almost chaotic process, a sort of roll of the dice, with many planetesimals, wannabe planets, forming, building up, and a competition, a sort of gravitational musical chairs takes place, in which the planets compete for their own space.
In this competition, some planets are flung out of the solar system, and some are tossed toward the center. It's believed some planets crash and burn on their parent star, while others survive in a close but stable orbit. These survivors are the hot Jupiters. The discovery of the hot Jupiter circling 51